to the Nature Center and to this seminar. Thank you very much for accepting our invitation and visiting us. Brief about Professor Davidson. Professor Eric Davidson is a professor and former director of the Appalachian Laboratory of the University of Maryland Center for Environmental Science and principal scientist at Spark Climate Solutions. He is currently visiting India as a Fulbright-Nehru Distinguished Senior Scholar hosted at Guru Gobind Singh, Indraprastha University. His research includes terrestrial nutrient cycling, greenhouse gas emissions from soils, global biogeochemical cycles, and sustainable agriculture. He is a past president and fellow of the American Geophysical Union, fellow of the American Association for the Advancement of Science, and the Web of Science highly cited researcher. Professor Davidson was a Jefferson Science Fellow, a program administered by the US National Academies of Science, Engineering and Medicine, where he served as a science advisor to the Office of Environmental Quality at the US Department of State. He is a lead chapter author on the Global Nitrous Oxide Assessment by UNEP. He currently serves as a senior editor for AGU Advances. Professor Davidson received his PhD from Department of Forestry at NCSU and worked as a postdoctoral researcher in soil microbiology at the University of California, Berkeley, and at the NASA Ames Research Center. He worked for 22 years at the Woods Hole Research Center, including a term as president and executive director. He published 2 books for the general public on environmental economics. That is, You Can't Eat GNP in 2000 and The Science for a Green New Deal, Connecting Climate Economics and Social Justice in 2022. With these brief words, I request Professor Davidson to deliver his lecture. Please.
Okay, shall we test this out? You hear me okay? Good. Well, thank you for that kind introduction, and thank you for inviting me here. It's quite an honor to be here. So I'm currently enjoying this wonderful opportunity as a Fulbright-Nehru Fellow. And this is a program I hope most of you have heard about. If you haven't, I would encourage you to look into it. It's a cultural exchange program between the United States and many different countries of the world, but I think the one with India is probably one of the biggest, if not the biggest. There are over 100 American scholars currently studying in India, and I think a similar number of Indian scholars studying in the United States. And it goes across disciplines from science, engineering, humanities, the arts, and it goes across career stage from undergraduate to senior faculty. And there's some postdoc opportunities and so forth. So it's a great opportunity of just to take advantage of the expertise in each country and learn from each other. It's also a great cultural experience. And one of the observations that I've made giving talks like this in various institutions across India is that the students always like to sit in the back, and the same is true in the United States. You know, it seems like everywhere you go, that's what happens. Handful of faculty in the front and all the students in the back. Anyway, today I'm here to talk to you about the Global Nitrous Oxide Assessment, which was published a few months ago by the Climate and Clean Air Coalition, which is part of the United Nations Environment Program. Nitrous oxide concentrations reached 338 parts per billion in 2024, and that's about 25% above the concentrations prior to the Industrial Revolution. In this graphic, you can see the concentrations in the atmosphere going back 2 millennia. In the blue diamonds, it's from concentrations taken from air bubbles in ice cores. And you can see that for about 1,800 years or so, it bounced around a little bit, but more or less was stable. And that means that the sources of nitrous oxide and the sinks of nitrous oxide were more or less in equilibrium for that period. But starting with the Industrial Revolution in the 19th century and accelerating into the 20th century and still accelerating in the 21st century, nitrous oxide concentrations in the atmosphere have gone up. In fact, the rate of increase per year, the number of parts per billion per year, is still increasing. It's now the third most important greenhouse gas. It is 300 times more potent in terms of radiative forcing per unit mass than is CO2 or when integrated over a 100-year time frame. It stays in the atmosphere for over 100 years. So what we're doing now will be with many generations to come in terms of the consequences. And it is now also the most important annually emitted stratospheric ozone depleting substance. And I'll talk a little more about that later. So where in the world is this nitrous oxide coming from? Well, all over the world, but as you can see from this graphic, the largest emitter is now in East Asia. North America is still a large emitter as well. And you can see that the trends do vary by region. Europe has actually decreased its emissions somewhat. Whereas East Asia, South America have increased their emissions. These are with emissions, total emissions, the y-axis being million tons of nitrogen for total for the country. The next graphic is kilograms per person, so per capita. And we see that somewhat different trends in that North America is now the largest per capita emitter, although that has been coming down in recent decades. Europe is also declining in per capita emission. East Asia is still increasing, but the per capita emissions are lower and the increase doesn't appear to be as sharp of a slope as with total emissions. But really, just about everywhere in the world, with the exception of Europe, emissions are going up, whether it's per capita or for the entire country. This graphic shows N2O in a shorter time frame from 2000 onward, and now the y-axis is teragrams of nitrogen as N2O. A teragram is 10 to the 12th grams. And what each of these little lines, faint lines, is a model run as part of the climate model intercomparison program of the Intergovernmental Panel of Climate Change in their 6th assessment. And then the somewhat darker lines are the means for each of these shared socioeconomic pathways that are being simulated. So these are pathways that involve some assumptions about economic development, about distribution of wealth and resources, and hence the term socioeconomic pathways. And you see that all but a couple of them in blue and purple at the bottom, all of the others show increasing nitrous oxide emissions through the first half of this century. And then on the far left, you see in the yellow dotted line and the black line, the actual measurements that we have, the best that we have available. The yellow is so-called top-down. Those are measurements of nitrous oxide in the atmosphere combined with a inverse modeling. In other words, you model backwards of what the sources must have been to get to that concentration in the atmosphere. Takes advantage of a little bit of a difference in concentrations between the northern and southern hemisphere and some seasonality as well. And the bottom up is using inventories, emission factors, and that sort of thing to try to get to add together emissions throughout the globe. And these two methods actually agree remarkably well, although I'm not showing the error bars of each. They each have fairly significant error bars. But the point I want to make here is that the measured emissions are already above all of the forecasted emissions from the shared socioeconomic pathways of IPCC. So we're already starting out worse than the worst case scenario in terms of emissions. Now, if you remember from the last graphic of per capita emissions, I didn't point out the black line is the average for the world. And the average for the world has been pretty steady at about 1 kilogram of nitrous oxide nitrogen per person. Well, it turns out having the number of 1 makes it very convenient for multiplying the human population, which is, let's see, in 2020, it was about 6 billion people. So if you multiply 6 times 10 to the 9th people times 10 to the 3rd grams per person, you end up with 10 to the 12th grams, which is a teragram. And so I can superimpose over the N2O emissions the human population and draw this red line, and I can do a pretty good job of predicting global nitrous oxide emissions just by knowing the increase in human population. So, and the reason for that, primary reason for that, is that nitrous oxide emissions are directly related to our production of food. There are other sources, as I'll show you, and there are other complications where emissions have gone up in one country and gone down in another. But on average, this works out pretty well, surprisingly well empirically, to show that as our population increases, our emissions of this important greenhouse gas and ozone depleting substance have also increased. This is a budget of nitrous oxide, and it's a bit of a busy graph. I'm not going to go through every arrow here. But I want to point out that the arrows on the right, colored in green, are the natural sources. Particularly tropical forests are a fairly large source. That's the fattest green arrow. There's a source from the oceans and the continental shelves. And as I said before, prior to the Industrial Revolution, the sources, which are about 12 teragrams, were roughly in equilibrium with the sink, which is mostly destruction of nitrous oxide in the stratosphere. Now, the sink has gone up a little bit since then because it's concentration dependent. But back before the Industrial Revolution, the sink was about 12 teragrams as well. So more or less it was in equilibrium. But now look on the left-hand side and all these orange arrows, these are all the anthropogenic sources that have increased since the Industrial Revolution. And you can see that the fattest arrow of those is 3.6 from agriculture. There are other sources like some fossil fuel in industry, wastewater treatment, and there's some offsetting effects of CO2 fertilization and climate change. I'm not going to go into those, but you can see that the anthropogenic emissions are now over 6 teragrams, and so the system is no longer in equilibrium, and nitrous oxide is accumulating in the atmosphere at an accelerating rate. To simplify that last graphic very simply in terms of anthropogenic sources, the majority is from agriculture with modest contributions from industry, biomass burning, and wastewater treatment. Now, why do we have the majority of N2O emissions from agriculture? Well, this is a graphic showing trends since the Industrial Revolution at the time on the x-axis. And on the y-axis, again, I have teragrams, but in this case, it's teragrams of nitrogen introduced into the biosphere, into the terrestrial biosphere. And the dark green segment on the bottom is the biological nitrogen fixation that occurs in terrestrial environments naturally. There are bacteria and fungi, often in symbiotic association with plants that create nodules in the roots of plants. And they are able to take dinitrogen gas out of the atmosphere. 80% of the air that we breathe is dinitrogen gas. It goes into our lungs and right back out. We don't use it. But these organisms can take it out of the atmosphere and we say fix it into reduced forms of nitrogen that are needed for life. to make amino acids, to make proteins. That amount has declined slightly over time as we've converted forests to agriculture. There's a little bit, that thin red line that comes from formation of nitrous oxide by lightning. Then there's the lighter green line, and that is biological nitrogen fixation from cultivated crops, such as mostly leguminous crops like soybeans, lentils, groundnuts, alfalfa. The yellow or orangish line is from combustion of fossil fuels, but the biggest increase is this big blue blob that we call the Haber-Bosch process of fixing nitrogen from the atmosphere through our industrial process. It was invented by German engineers and scientists in order to provide Germany with munitions during World War I. It then became used widely to make synthetic fertilizers after World War II. And you can see how big it has grown since that time, and projected to grow further by the middle of the century. This has resulted in a great boon to human health. Yes, there's still places where people are malnourished. Yes, there's still hunger, but that's usually because of war and natural disaster and inequitable distribution of resources. We actually produce enough food that if it were equitably distributed and not wasted, we could feed everybody. But this comes at a huge environmental impact, because this nitrogen that we're putting on our croplands to feed us is not staying there. On average, about half of it gets into the crop, and the other half goes into the environment, which results in eutrophication of estuaries. By eutrophication, I often mean expansion of algal blooms and such. And as the algae die, that consumes the oxygen as it's decomposed, and it creates what we call dead zones that fish and invertebrates, shellfish that can't move out of the area tend to die from lack of oxygen. There's nitrate in drinking water as nitrate leaches off of these agricultural fields. NOx, ozone, which is formed from the NOx through photochemical reactions in the atmosphere, and PM 2.5, those fine particulate matter that we breathe deeply into our lungs and causes respiratory disease. About 30 or 40% of those particles are made up of ammonium nitrate or ammonium sulfate. And so this is a nitrogen problem, even though it's often not spoken of that way in the popular press or even among scientists who are involved in air quality issues. As I mentioned, it's an important greenhouse gas. Also, what goes up in ammonium and nitrate in emissions to the atmosphere often gets rained down, downwind, and where it falls on forest environments, grasslands that are not accustomed to such high levels of nitrogen, and that can change the biodiversity of the plants and animals that can live and grow there. Although we're talking about too much nitrogen for most of these issues related to environmental issues and human health, I want to point out there are also places in the world where there's too little nitrogen for agriculture. And also, this isn't strictly a north-south issue. As you can see, there are the usual culprits of using a lot of nitrogen fertilizer in the Corn Belt of North America, in Western Europe. But you can also see that as a result of the Green Revolution, it's also very heavily used here in India, and also has become very heavily used in China, and to a lesser extent in Brazil. But sub-Saharan Africa still has too little nitrogen. Farmers there either don't have access to fertilizers, or if they do, they can't afford them. And so they are essentially mining the soil of nutrients. They're taking more out in their harvest than they're putting back in. And that impoverishes the soil, degrades the soil over time. It decreases their economic viability and their nutritional status. And so at the same time that we have to deal with too much nitrogen in some places of the world, we also have to be cognizant of there being too little in other places. Next, I'd like to talk about where all that nitrogen goes. We talk about fertilizers, and so we think of croplands, right? But actually, the vast majority of our crops are fed to our livestock. In this graphic, you can see that yes, we put in over 100 teragrams of fertilizer onto the soil. And there's also another 60 that comes in through nitrogen fixation of leguminous crops. But of the nitrogen that's taken up by our crops and our grasses, the vast majority of it is fed to our livestock. Only about 20% or less is fed to humans in the form of our grain, our rice, wheat, corn, fruits and vegetables, and that sort of thing. So we really have a very productive food system that could feed the world and is nutritious. And yet it is really based on animal protein more so than on plant protein in terms of human consumption. Now, I show 57 teragrams going back from livestock to soil. For one thing, there are no air terms on this. It would make it look too busy. And there are very big air terms on all these. I believe in mass balance, so the numbers should add up. But I've become convinced that that 57 number is wrong, that there must be another loss mechanism of manure washing away from places where it accumulates or is stored, going into water bodies. Because the data show that in most countries of the world, including India and the United States, only about 20% of the manure is recycled back onto cropland. So there's a tremendous opportunity there for using that resource more effectively. So what can we do about this? Well, we can try to come up with ways of using nitrogen more efficiently in the cropland. NUE stands for nitrogen use efficiency. I am going to talk near the end about some more transformative changes of trying to think about new ways of changing our food production system, getting nitrogen more directly into the livestock feed rather than via the plants that we grow on croplands. And then, as I just mentioned, nearly all countries in the world need to work on the technology and the socioeconomic drivers of how we can use manure more effectively. And this would also include, for that matter, human waste. Well, the reason that that only about half of the nitrogen that we apply to our soils gets into our crops is that our food production system is, as it currently stands, is very linear and very leaky. So I'm using this metaphor of a fluid flowing through a pipe. If on the left-hand side we put all of our nitrogen inputs, the synthetic fertilizers, the manures, the natural nitrogen fixation, feed that into our crop production pipe, and you can see that that pipe is leaky because the bacteria and other organisms that are involved in the soil or in aquaculture and in the oceans, they produce small amounts, but it really adds up given how much nitrogen we put through this system of ammonia, nitrous oxide, NOx, and some of it is soluble going into groundwater and surface waters, particularly as nitrate and dissolved organic nitrogen. And then we take most of that and in the blue arrow, feed it to our animals. And then once again, we have another leaky pipe that produces the same components, gaseous and liquid forms of nitrogen that go into the atmosphere. So at the end of the day, of 100 units that we feed into our food production system, somewhere around 10 to 20 units go into crops that are actually consumed by humans, if you're a vegan. But if you're consuming animal products, then it would really only be on average maybe 4 out of those 100 units. So it's a very inefficient, leaky system. Of course, this is painting with a broad brush. These are averages. There are some crops that are more efficient than others, some animal systems that are more efficient than others, but this is a broad overview. Now, from this nitrous oxide assessment, this is one analysis that was done from a Chinese colleague, Baojing Gu, looking at a meta-analysis of publications of how various forms of nitrogen pollution could be reduced from agriculture. And so, as in meta-analyses like this, on the x-axis, a negative number means a lower emission, and a positive number means a higher emission. And you see ammonia, nitrous oxide, NOx, nitrogen leaching, that's nitrate to groundwater, and runoff, that would be surface runoff. And then on the far right, you have yield and nitrogen use efficiency. In those cases, you would want it to be on the right to increase nitrogen use efficiency, increase yield. And then on the y-axis, you see various different agricultural practices. EEF stands for enhanced efficiency fertilizers. These are things like nitrification inhibitors and urease inhibitors. In the Indian context, this would include neem-coated fertilizer, urea. And then there are some amendments like biochar have been shown in some cases to reduce nitrous oxide emissions. And then the next four are what we call the 4 R's, putting on the right rate, the right type, the right time, and the right place. And this has been proposed by the fertilizer industry as a way to voluntarily get farmers to use fertilizers more effectively. And you can see that in most cases, these various approaches do result in lower emissions. But the question is, how do we get farmers to adopt them? These are mostly studies from agricultural experiment stations, a few of them from actual on-farm experiments. But this shows the potential. It is not showing us what actually is being accomplished. And as I said, nitrous oxide just keeps going up and up and up. So although we know about these, that doesn't mean that they're being applied and achieved. So in this assessment, we looked at potential mitigation by sector. On the left is the agriculture sector. As I said, that's the biggest source. And there is the baseline of 2020 emissions. And if you're looking carefully, you'll see the numbers on the y-axis are a little bit different this time. And that's unfortunate. It's because this time it's the mass of the nitrous oxide molecule, including its oxygen, that's shown on the y-axis, as opposed to the other data I've given you, just nitrogen. That's beside the point, really. The main thing I want to show you is the differences in that without mitigation, the projected 2050 reference scenario is a very significant increase in emissions. If we adopt those technical approaches that I showed you from the last slide, if they could be universally adopted or widely adopted, we could reduce emissions not only below what's projected, but below current levels. And then there's another one, a scenario called technical and societal. And basically what that is adding on dietary change, convincing people, particularly of high-income countries, to consume less meat and dairy products on a per person. And that gets you a little bit further. On the right you notice that the value on the y-axis on the graphic on the right is an order of magnitude smaller, because the emissions and the mitigation potential from the industrial sector, production of adipic and nitric acid, is much smaller. Nitric acid is used to make some fertilizers, also to use to make munitions, and to use to make adipic acid. Adipic acid is used to make nylon, and it's surprising how much nylon we have in our clothes, probably maybe the material used for these seats. It's in coatings of cables in automobiles. It's very widely used. But this differs from the agricultural sector in that there are technologies that are already available and affordable that we could essentially zero out this source of nitrous oxide. It's not as big of a source, but it could be zeroed out relatively quickly. And this is an example of doing, not only looking at the size of the potential reduction shown here in the first two columns, but also a range of abatement costs that we were able to obtain from the literature. And you can see that the abatement for the industrial sector is generally less than $20 per ton of CO2 equivalent. N2O and methane are often converted to CO2 equivalents in terms of radiative forcing on a 100-year timescale, in order to have a common currency, since most of the carbon trading is done in terms of CO2. But we can use the carbon trading markets potentially to address methane and N2O. Anything less than $50 a ton, even anything less than $100 a ton, is generally considered feasible. And less than $20 a ton is really very affordable. It's mainly China and the US that are still emitting N2O from the industrial sector. And there is some progress being made to reduce those emissions. But as I said before, the largest potential and the largest challenge is in the agricultural sector. And you can see there that the estimated costs are anywhere from $20 to $180 per ton of CO2 equivalents. And so while it's the largest potential, it's also the most challenging, both socially and economically. And so we need R&D to help come up with new solutions and to bring the present solutions to a more reasonable cost. Now, I've often mentioned N2O in the same graphic or in the same sentence as I do the other nitrogen pollutants. And that's a really important take-home message, because the things that we can do to abate nitrous oxide emissions are very likely, on average, not always, but usually, to abate other nitrogen pollution problems. And this is both an opportunity and in some cases an obstacle. So for instance, what this graphic shows in the deeper orange is the warming effect of nitrous oxide on the left. But NO and NO2 also form tropospheric ozone, and that too has a warming effect. But they also form aerosols, and aerosols reflect radiation back into space. So aerosols have a cooling effect. But of course, we need to clean up PM 2.5 for human health purposes. We've been cleaning up sulfur emissions for that purpose. And as a result, we've probably had some cooling effect, some warming effect as a result of decreasing sulfur emissions. And as we decrease PM 2.5, there probably will be a warming effect from that will counter the cooling effect of decreasing N2O. So it's complex. Unfortunately, that's an unfortunate message to have to give to the public. Generally, scientists are advised not to say, well, it's complex. We like to have simple solutions, but in this case, there isn't a simple solution, in that abatement is actually likely to cause some short-term warming before the long-term cooling of the reduced nitrous oxide emissions becomes more dominant from this long-lived greenhouse gas. And there's some other complications, like ozone damages plants, that reduces carbon sinks, but nitrogen deposition in moderation can increase photosynthesis, that can increase carbon sinks. But we need to have all of these things synthesized together and presented, which is what this assessment attempts to do. So we then, at the end of the day, say, well, even though nitrous oxide doesn't directly affect human health, if we abate nitrous oxide, we will also be abating PM 2.5, and there will be some direct effects on human health, such as projected decreases in cumulative premature deaths due to ozone pollution in the troposphere and due to PM 2.5. Recent estimates show that there are about 9 million people globally who die prematurely due to various forms of pollutants. And about half of that is due to ozone and PM 2.5. We often don't recognize that as, elderly grandparents and uncles and aunts dying of that particular disease. They maybe are dying of complications of a respiratory disease, but it actually can be traced back to our use of nitrogen. And then there are other benefits as well. Now, this is another cost-benefit analysis where in below the line are the reduced costs, the benefits of saving the cost of applying so much fertilizer if we use the fertilizer more effectively. It's offset somewhat by implementation costs. And then above the line are all these monetized costs of things that are not really traded well in our market economy. I've already mentioned the human health benefits shown here in the green bars of, for instance, reducing PM 2.5. They're all, or excuse me, that's in the bluish purplish bars. There are also ecosystem benefits. There are also potential yield benefits by using the fertilizer more efficiently, and in the case of sub-Saharan Africa, providing more fertilizer. So you can see that in places like China and India, there are very large ecosystem benefits and health benefits. In places like sub-Saharan Africa, there's a larger yield benefit, crop yield benefit. But these are all estimates based on we academics applying a dollar value to things that are not traded in the economy. And so if we are relying on the private sector and the economic system, these are not going to be drivers of change. It's only if we can use this information to influence our policies so that our policymakers understand that there will be a net benefit to society, reduced health problems, reduced climate challenges. It's many different kinds of challenges if we do this abatement, but it won't be driven by pure market economy drivers. Finally, I want to get back to ozone, since I know a number of you work on that, this time stratospheric ozone. Since the Montreal Protocol, we've been successful in reducing emissions of chlorofluorocarbons, hydrofluorocarbons, and other ozone depleting substances. There's still a legacy in the atmosphere from emissions from the 20th century. But in terms of new emissions, we've reduced all these, the CFC 11, 12, and all the others that are shown here on the right-hand side, to a point where those now sum up to the same value as N2O. And so the N2O is by far the largest newly emitted ozone depleting substance. That's what I just said. And then another interesting outcome of this, which is beyond my area of expertise, but I'll repeat what the stratospheric ozone chemists reported in this assessment, is that due to the complex stratospheric chemistry, in the event that society is able to limit the first two important greenhouse gases, methane and CO2, in order to avoid catastrophic climate change, but do nothing about N2O, the chemistry is such that ozone depletion will actually go up. Another way of saying that is the efficacy of N2O as an ozone depleting substance goes up when you decrease concentrations of CO2 and methane. So again, it's a complex system that we have to understand that complexity to really understand what is going on and what is at stake. So I mentioned at the beginning, we already know about what to do, but they're a little bit too expensive for us to do them at scale at the moment. We're also thinking about how can we really rearrange or reimagine our food production system, because we have to have nitrogen to feed people. There's no way around it. You have to have, protein is necessary for human health. And to make protein, whether it's in a plant or an animal, you have to have nitrogen. So how can we make our agriculture, our food production system, less linear, which is nitrogen 1.0 shown here on the top, where we make our fertilizer in a factory, we apply it to crops, feed the crops to animals, and feed the animal products to humans. And at each step along the way, there are large losses to the environment. How can we change that to make it more circular and more targeted? So we're talking about this as a vision of nitrogen 2.0. It's not going to happen next year. We'll be doing well if it happens next decade. But I think we can work towards that. One of the ideas is essentially to skip a trophic level. Right now, we're broadcasting our fertilizer on the croplands, we're growing crops and feeding it to animals. It's very inefficient. If we could put more of the nitrogen directly into the animal feed, we still have to grow crops because they still need calories. But we could grow crops that have a lot less nitrogen, therefore they wouldn't need as much fertilizer. Also, where crops like maize are used for biofuels, you don't need nitrogen in the maize grain to make a biofuel. So we could use a lot less fertilizer to be growing those grains that are fed to the animals if we could put more of the nitrogen directly into the animal feed. And I'll show you an example of that that's happening here in India. Second, we can, with crop breeding, we can come up with varieties of our major crops that require less nitrogen. When varieties, for instance, for rice here in India were selected during the Green Revolution, they were selected for yield, not for nitrogen use efficiency. And my colleague at Guru Gobind Singh Indraprastha University is now doing the genetics to try to select varieties of rice that maintain high yield, but also have higher nitrogen use efficiency. And as I mentioned in the beginning, manure recycling is a challenge everywhere in the world, and that needs technological developments, but there's a huge potential of being able to use manure more effectively, which would reduce the demand for fertilizers. So I said that this idea of skipping a trophic level, I initially thought that this was an idea mostly for Western Europe and North America to develop, that this was going to be something that, high-income countries would invest in resources in dealing with. And I discovered that actually the conditions are really good here in India to develop this kind of technology, that my assumptions were wrong. And this is an example from a company near Delhi that actually produced the first green ammonia plant in the world in Rajasthan. And it is now investing heavily, it and other companies are investing heavily in large billion-dollar plants for green ammonia, mainly for use as a marine shipping fuel. But they're also experimenting with it for use as a fertilizer. And the story goes something like this. You've probably heard of green hydrogen. And that's basically taking energy. It could be from a solar panel, from hydropower, from wind turbines, running an electrolyzer to split water into hydrogen and oxygen. Now you have green hydrogen. You can then combine the green hydrogen with nitrogen in the same way that we make synthetic fertilizers now with the Haber-Bosch process to make green ammonia. It can be used as a fuel. We could talk about that later if you want. I don't have time now, but also can be used as a fertilizer. They're experimenting with, in this case, growing some maize or corn, but really only to harvest or extract the syrup. They're not really interested in the nitrogen content of the grain. So they've said this could possibly be used with sugarcane. It could also be possibly used with food wastes, where you can get a carbon substrate formed. And then they've developed a fungus that is able to grow in fermentation, in a fermenter, with this corn syrup, and they add more of the green ammonia to the fermenter. So the nitrogen is not coming from a plant, it's coming from the production of green ammonia using renewable energy. And from that, they produce fungal biomass. They call it mycoprotein, myco standing for fungi, that is enriched in protein and is highly digestible And they've tried it out with focus groups. They've taken the flour and added it to chapatis and biscuits and tried it out with focus groups. And they found that there's no adverse taste. And so essentially what they're doing now is they found that 70% of this is fit for human consumption, and the other 30% would be used for feeding livestock. So that vision of skipping a trophic level is actually being developed here in India before it's being developed in other parts of the world. The business model, I think, depends on the government subsidizing this enriched flour in order to make it available at scale in products like the flour used for making chapatis or to biscuits or other products. So it remains to be seen whether this would actually happen, but I wanted to present this as the kind of idea that we're thinking of, many people are thinking of, to try to go from nitrogen 1.0 to nitrogen 2.0 to make our food production systems more efficient and effective. So I'll leave you with a few main points paraphrased from this nitrous oxide assessment. Without abatement, global anthropogenic N2O emissions will increase by about 30% by the mid-century. But mitigation measures available today could reduce those anthropogenic emissions below current levels, but at present, most of them are too costly. That mitigation requires a sustainable management approach across scientific disciplines, across policy ministries, across sectors in the private sector. It will result in improving air quality now, such as NO2, ozone, and PM 2.5. It can reduce eutrophication of water bodies and avoid nitrate contamination of drinking water. So there's a bunch of co-benefits from abatement of nitrous oxide. But interestingly, the lower PM 2.5 would have a short-term warming, but reduced warming will occur in the second half of the century due to the decrease in nitrous oxide's long residence time in the atmosphere. So it's a complex story, but it is one that we can sort out and present appropriately to policymakers. And I hope I've done a decent job of presenting it to you today in an understandable manner. Thank you for your attention. I'd be happy to answer any questions.
India's focus is now shifting back on the traditional natural farming practices. So how feasible is it if it is implemented on a global scale?
The question is, how feasible is natural farming? Do you want to define natural farming practices for me a little?
Natural farming, which mostly is farm sustainable methods, like for example, using the animal waste, animal manure, converting them into products, natural fertilizers. It's a concept of the farm sustainability.
Right. Well, I think, as I've said, recycling manure is really an important part of this nitrogen 2.0 concept. I don't think we're going to be able to feed 8, 9, 10 billion people without use of synthetic fertilizers. But we certainly need all the tools in the toolbox. And by learning to recycle manure, perhaps even human waste more effectively, we could greatly reduce the amount of nitrogen fertilizer that we need to use. In local farms, in certain farm situations, you may be able to do away with synthetic fertilizers altogether. And there is a growing market for so-called organic produce. In most cases, it's kind of peri-urban of selling that produce to the people who have the disposable income that they can buy more expensive organically grown produce. And that's great. I think it's wonderful. But we're also looking for solutions in which the sub-Saharan African farmer, for example, can double his or her production by using only a few bags of fertilizer. Most sub-Saharan farmers don't have access to high-quality manure because just as they are malnourished, their animals are malnourished. And so they don't produce good manure to fertilize the crops. And maybe there's been a lot of effort put in to make green manure, in other words, mulching or compost. And that works as well, and that can be very helpful. But you have to have a source of it. And that competes with the farmland that you're using to growing the crops. And if a farmer only has a couple of acres that he's inherited from his parents, then you can't devote more of that to growing the green manure. So my answer is that yes, to the extent that we can adopt any of those natural growing processes that's financially and economically and logistically possible, it's a tool in the toolbox that we should use. But I don't think we should think of that as a solution globally.
During the talk, he mentioned that if there is a reduction in methane emissions and carbon emissions, there is a possibility of having N2O emissions increase. So how could you reduce all of them together?
First of all, let me clarify. What I meant was the effect of the N2O in the stratosphere would be higher. So I didn't say that if we reduce CO2 and methane emissions, N2O emissions would go up. What I meant was that the efficacy of N2O as an ozone depleting substance would be greater in the absence of, under lower concentrations of CO2 and methane. Okay. But you're right, we do need to look at reducing emissions of all three gases simultaneously. And green ammonia, for example, is one of the examples where if we can synthesize fertilizers with renewable energy, we could reduce 1 or 2% of global CO2 emissions. So the fertilizer industry is a big source of CO2 emissions. So there are linkages between carbon and nitrogen. Also, better manure management to reduce N2O emissions could also reduce methane emissions. Better livestock nutrition could reduce the difficulty of managing the manure and at the same time reduce enteric methane emissions from ruminants. So there are many, many linkages among these different gases. There are a few trade-offs. There are some examples where you increase one, you decrease one, you might increase another. So we have to be very careful.
Thank you.
Sir, just correct me if I'm wrong. I just heard by you saying that because of the depleting soil health, the microbiomes are not fixing that much amount of nitrogen like that. So would it be possible that we can develop strategies to improve the soil health or make some gene alterations in these microbes so that will help in the process?
Right, definitely. In fact, there's something that is called regenerative agriculture, which is not the same as organic agriculture. It doesn't exclude the use of fertilizers, but it does have a few other important components. One is to minimize tillage. That improves soil health. Another is to keep a cover crop or some sort of crop over the soil year-round if possible. That increases the amount of plant inputs of carbon into the soil. Another is to try to integrate crop and animal production systems. So right now, especially in high-income countries, the animal production systems are very centralized, intensified, often located a long ways away from the crops. And so it's very difficult to get the manure back onto the cropland. If they can be integrated back into the same regions, it would be easier to use the animal waste. And also, the animals can at parts of the year, if there's a cover crop, the animals may graze on the cover crop, which gives the cover crop now an economic value that it didn't have before, and it substitutes some of the cost of animal feed. So there are lots of things, and the animals are there on the cropland dropping their waste. So there are a number of things of what we fall in the category of regenerative agriculture that could improve soil quality. Here in India, I think I mentioned this story earlier today to a smaller group. I had the opportunity to visit some small farms in Maharashtra state, and one farmer who had been, his family had been farming for generations. They'd been growing sugarcane, and he said that his grandfather primarily used manure as a source of nutrients. But now he primarily uses synthetic fertilizers because he doesn't have access to manure. And he's noticed that his yield is lower than his grandfather's yield. And the soil testing shows that even though he's putting on a lot of fertilizer, it's low in nitrogen. And the reason it's low in nitrogen, a soil scientist would answer, well, it's lost its organic matter. You're no longer putting in manure and you're tilling it. You're losing the organic matter, so there's nothing to hold on to the nitrogen that you're putting in. It just goes right straight through to the groundwater or goes up as nitrous oxide. I'm not saying that he should not use fertilizer, but the fact that he's using only fertilizer and no manure, which has organic matter, it not only has nitrogen, it has carbon. It's organic matter. And that improves soil quality. So yes, you're absolutely right. We should be focusing on soil quality. That will have a lot of benefits in terms of carbon sequestration, nitrogen mitigation, and probably improve yield and improved economic viability for this farmer.
As you told that the nitrogen cycle is linked with other biogeochemical cycles. If nitrogen oxide emission is reduced through sustainable agriculture practices, can we reduce the negative effects of the carbon cycle?
Reduce the negative effects of what? I'm sorry?
Carbon cycle.
Carbon cycle. Well, yes, I think many of the mitigation approaches to reduce nitrous oxide emissions from soils would, as I was just saying, improve soil quality and the carbon content of the soil. So one of the ways of decreasing N2O emissions is through additions of biochar, through using cover crops, through returning crop residues onto the land, returning manure onto the land. All of these things would help retain nitrogen or use nitrogen more efficiently and build up soil carbon. So there are linkages between the carbon and nitrogen cycling, and that's just one of many linkages between them. Another one, as I said, is just production of the fertilizer in the first place. Fertilizer, as we currently produce it using natural gas as the source of hydrogen to make the ammonia, it releases a lot of CO2 into the atmosphere. 1 or 2% of global emissions is just from fertilizer production.
Thank you, sir. Thank you for the insightful presentation. So, what I understand is when we talk, like we need to look at the comprehensive approach. Like we were discussing during the discussion interactions that starting from looking for alternatives like animal-based, plant-based, and even human-based alternatives for manures and fertilizer, to improving the nitrogen use efficiency through liquid nitrogen. And the one we, like in India, we have this neem-coated fertilizers. And then it was interesting to know the cutting of tropical levels. That was an interesting study. And then what I also feel is, would it be possible, like we have this crop water budgeting, like based on the soil status, based on the water availability, we say that so we'll not do this. Some crops like sugarcane and rice is not recommended for water scarce regions. So I'm just thinking, would it be possible to have such things for soil nutrient status. Based on that, the nitrogen status, can we also do such kind of crop budgeting or crop planning, and can it be included in the, I mean, how practical it is to do that? That's my question. Thank you.
Well, yes, I didn't talk about the nitrogen-water interactions. There's only so much you can do in an hour presentation, but you're absolutely right. There are very strong nitrogen-water interactions. Work in sub-Saharan Africa has shown that if you just provide those farmers a small amount of nitrogen fertilizer, their crops actually become more drought tolerant because the crop is healthier and it can withstand a bit of a drought. And in East Africa, droughts happen every few years, and so that's very important in terms of the food security. In the Indian context, you know, I'm a little hesitant as an outsider to be saying what should be done in India. I don't think that's the appropriate role for me, but I will repeat some things that I've heard from my Indian colleagues. For instance, does it really make sense for the government to be providing a guaranteed price for rice when you're now producing so much rice that you're exporting it, but you're importing lentils? Previously, this balance between grains and legumes has gotten out of balance for India. One of the reasons that emissions are not, well, let's see, let me rephrase this. In the United States, we grow a lot of soybeans because, well, until recently anyway, until this year, we sold a lot of soybeans to China. I don't know if that's going to continue or not. But we have a pretty healthy ratio of grain to legumes. We still have significant emissions of nitrous oxide and still significant nitrogen leaching. But it is nitrogen use efficiency has increased in the United States. I think because we've maintained this balance between legumes and grains. And the same would apply to water use. Does it make sense to grow crops where you have to, where the groundwater is depleting, or put in solar-powered pumps where you have groundwater problems? So now all of a sudden, the energy to run the pump is free, and so it's not just being turned on when the energy's on, and the government can no longer control how much irrigation occurs because now the pumps can go all the time, right? Almost. I'm exaggerating probably. So yeah, if you take a big picture look at what would make sense if you were a benevolent dictator, is what would make sense if you were an engineer that could plan this system. But of course, mixed up in that is a lot of complicated politics and economics. It doesn't really make sense to be subsidizing urea to the extent that it is subsidized. China has backed off on its subsidies. It's still subsidizing. But China had the same issue about food security as India did. And it heavily subsidized fertilizers until it got to the point, and kind of the turning point maybe was the China hosting the Olympics. And they decided they had to clean up their air for a little while in order to have the Olympics. But they also had huge water pollution problems. And so they have sort of turned the corner in terms of reducing their subsidies and introducing measures that will help farmers reduce their nitrogen losses. Of course, that's an authoritarian government that can turn the corner when it wants to turn the corner. And so every country in the world has a different circumstance of the politics, the economics, the history, the consumer demand, the culture, the food system. And so it's up to the civil society of each country to come up with, you know, the right combination of solutions that include water, nitrogen, phosphorus, all of those things. So thanks for your question, but it's a very challenging question from a political and economic point of view.
Thank you very much for your excellent and insightful lecture. Our faculty and students and staff got benefited. Thank you again for visiting us as a token of our appreciation. Like
Thank you. Thank you.
Thank you. Join for tea.
Okay.
If you have any other questions, thank you.
You might find this humorous. One time I was giving a talk like this, and your counterpart forgot to come up and get it for me. And I walked off and I went into the men's room with the microphone on and kept talking and making noises. It wasn't pretty. Pardon me? I'm just gonna...